Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. So we're thrilled to have Yash Deshpande here. He was an intern with us, so some of you will know him from there. And he will be talking about computational limits in statistical inference, hidden cliques, and sum of squares.
Okay. Thanks everybody for coming. Thanks for the introduction, and it's great to be back after a few years. I always like visiting Boston. So I'm going to be talking about computational limits in statistical inference. And in a talk like this, it's almost a cliche to start with something of the form that we live in a world of big data. So I'm not going to start that way. Instead, what I would like to do is, start. I'll just explain a few examples which illustrate what I think are the important trends. So what you see here is an MRI machine. The first example is about medical imaging, and some of you might have had the chance to be inside one of these machines. Unfortunately, if you haven't, the likelihood is really high that at some point in the future you will. But the point of the machine is basically to take medical diagnostic images of the kind that you see on the left. Now, we won't go into the physics of how the machine really works, but it suffices to say that each measurement of the machine gives you 1 point on the Fourier transform that you see on the right. So now, these machines, if you've been in them, it can take a lot of time to collect all of the points in the Fourier transform, so you have to stay extremely still for about 10 minutes or so. This is hard enough for adults. It's completely impossible when you start thinking about infants or rambunctious little toddlers who will want to wander about all the time. There are
Pets.
or
They
pets.
gotta put pets down, so it's thousands of dollars just for
Right.
the anesthesia.
Exactly.
We know this.
Exactly. There is other applications like like taking the MRI of a beating heart, and if your heart is beating, then it's impossible to image this. The breakthrough that happened about a decade ago was to realize that you can get away with just taking a few points on the Fourier transform. So instead of actually collecting all of the points, which will require you a long time to collect, you just subsample some of the Fourier coefficients and collect them. So say you collect these red dots over here. This takes a much shorter period of time because the machine doesn't have to run as much. But then the question is, well, you now only have a few of the measurements. Can you still get medical quality images? And really the breakthrough work by Donahoe, Candace, and others was the realization that you can use L1 based methods or convex relaxations to obtain very good quality reconstructions even from very few measurements. My second example is recommendation systems. So a few years ago, Netflix ran one of the early machine learning challenges, which nowadays are very popular if you've seen Kaggle, etc. They released a data set of movie ratings that people had given. So for instance, this is a cartoon of the data set. Every column corresponds to a movie, and every row corresponds to a user. So maybe the first user is Jennifer, who, I don't know, maybe happens to be a sci-fi buff, so she really likes Martian and the new Star Wars movie. And perhaps the second user is me, who doesn't happen to watch a lot of movies, and maybe I didn't even enjoy The Godfather very much. So the question is, you're obviously given just a small set of the ratings because not everybody is going to go and watch every movie. So given just a small set of the ratings, can you fill in the blanks? Can you infer the rest of the ratings and use this for downstream applications like recommendations? And during the prize, there was a lot, because of the Netflix prize, there was a lot of work that was done on problems of this kind and more generalizations. And the realization is that convex relaxations of one or the other form are extremely useful and in fact formed part of the solution for even the winning Netflix prize challenges. I believe now it is used also in the company's recommendation system. My third example is instead from genomics. So what you see here is a representation of the results of a study that was done about more than a decade ago. It was reported in PNAS. What they did was they assayed gene expression levels from a number of patients. And basically what you have here is a genes times subjects matrix. Every row corresponds to a specific gene and every column corresponds to a subject. And the subjects are of two types. The blue ones are actually lupus patients. If you've watched House MD, lupus is an autoimmune disorder. I don't watch House MD, so I had to look it up on Wikipedia. The green ones, the green columns are actually healthy control patients, which they also assayed. What they found was that there were a certain subset of genes. These were related to a certain immune pathway called the interferon immune pathway, which had abnormally high expressions in a small subset of the lupus patients. So within this red splotch that you see over here, there is actually hidden an even darker red splotch. And these patients which had these abnormally high expressions, they were actually the more critical patients. They were the ones with the more severe versions of the disease. The disease had affected their liver, kidneys, etc. This is obviously, findings of this kind are important because you can use it for targeted medication. It tells you a little more about the mechanism of the disease because lupus is an immensely complicated disorder. We don't know a lot about this. So the question is, given this large messy data set, can you figure out patterns of this kind? Okay. So there's really an important difference between the first two examples, which is medical imaging and recommendation systems, and the third one, which is that in the first two cases we have good estimators. These are often based on convex programming, but not necessarily. And these are good in two senses. They have good statistical guarantees. They are statistically efficient. They take advantage of all possible statistical information that is present in the data set. And because, for instance, if they are based on convex programming, you can actually compute them. There are fast algorithms to compute these things. For the genomics example, you don't have this scenario. And in many other examples of this kind, what you actually have is that there are either estimators that are statistically very efficient, but we don't know how to compute these quickly, or the other way around, in the sense that you have something that you can actually program on your computer, but it is not as good in statistical performance. So this is really the main question that I would like to think about in this talk, which is that how do we characterize computational complexity in statistical estimation settings? This is actually an extremely broad question, and in reality, because people are extremely clever in coming up with variety of algorithms and doing computation in very, very interesting ways, this is one of the probably the most difficult way to earn $1 million that you can think about. So instead, I won't try and do that, but I'll try and do something a little bit simpler, which is just talk about one example, which is the hidden clique problem, because it in reality is a prototypical example of really this phenomenon where computational constraints are more onerous for a statistical estimation problem. So, okay, so this is a plan for the talk. I'll set up the problem in the beginning, and then for a while we will talk about what are the things that you can actually do. What are the good algorithms? Really there are spectral algorithms and a little bit of twists on that, and I'll mention a result there. After that, we'll change gears and move to instead trying to think about computational hardness. So this is kind of the other side of the story, and I'll talk about the sum of squares relaxations just as a tool to characterize the complexity. And in the end, I'll just mention some other things that I have been interested in the past and what I think would be cool to think about. If anybody has any bright ideas, I would be very happy to hear. Okay, so let's go back to the genomics example. Remember that there is, hidden within these rows, there are these black rows which correspond to genes that have these abnormally high expressions. And let's just do something very simple. Let's try and construct a graph that summarizes this data. Okay, maybe we can see something in the graph. So the graph will contain two kinds of vertices. The vertices on the left correspond to genes, so they correspond to each row, and the vertices on the right corresponds to the patients. And I will connect a gene with a patient if I see that there is a very red dot in this matrix. So if there is,
do you have weights on them corresponding to how red it is or not?
in principle, yes, but for now, let's just think that there are no weights. Okay, I'll just do a very simple thing. Okay, so you pick a threshold, and if it's below the threshold, you don't put an edge. If it's above the threshold, you put an edge. Okay, so maybe the first gene is not an interferon gene, so it doesn't have too many edges. The second one has a few more edges, and so on, and now you build the graph. And really what happens is that the gene signature starts becoming visible as a dense subgraph of this graph. Okay, and what you would want to do is, given the unlabeled graph, the graph without all of the colors, you want to find that dense subgraph. Maybe that tells you which of the genes and which of the patients are involved. So let's take this a little bit seriously. I'll start with a mathematical model. So instead of having two types of vertices, I'll just symmetrize the problem and have one type of vertex. Really, the results will probably go through just as is, but it's easier to talk on in this setting. So the null model, or the null hypothesis, is that the graph is a graph on n vertices, and it is a purely random Erdos-Renyi graph, in the sense that between every pair of vertices, an edge exists with probability 1/2, independent of all of the rest. Okay, so this is similar to it's just a simpler version of the bipartite one we had earlier. And instead, the alternative hypothesis contains k vertices out of n, which are colored here in red, and they're all forced to form a clique. So all of the edges within those k vertices are connected, but the rest of the graph is generated as random as before. Okay, well, there's two kinds of questions one can ask. The first is just detection. Can you distinguish between these two hypotheses? You're given a graph, can you tell me whether it is generated according to this model or the other model?
How does is k constant, or it grows with n in some way?
K might depend on n in general.
It should be for this to be statistically possible, right?
Yeah.
Yes, indeed, indeed.
And the k points are chosen.
Think of the k points chosen at random before the graph, so they're not dependent on the graph structure. Or think of generating the graph conditional on a certain subset of k vertices being a clique. These two are the same distributions. The second problem is the estimation problem, which is obviously harder than the detection problem, which is that given the graph, can you find me if the clique exists, can you find it for me? Okay, who can find the clique in this graph?
Yeah.
Okay, now the real problem is, of course, things are never ordered and they're never colored. No, but the edges were dark. The edges were fatter, so maybe Adam could even there. So Adam can still find the cliques in this one. So maybe we should just stop here. But okay. So this is how you will receive the data set, and now you want to do the distinction. There's a useful interpretation in terms of the adjacency matrix. What I will do is I will encode the presence of an edge by a +1 and the absence of an edge by a -1. Okay. So under the null hypothesis, my adjacency matrix, or the adjacency matrix of the graph, is a purely random, is a symmetric matrix with purely random independent signs. So it's filled with Rademacher independent random variables. Under the alternative hypothesis, instead there is a principal submatrix, here the submatrix shown in blue, which is all +1s, and then the rest of the stuff is ±1s as before. Okay, and then the detection problems is the same as what we had before. So as Boaz mentioned earlier, what is the thing that you need to at least solve this in principle? Is there any algorithm that will solve this for certain values of k and n? And if you think about this for a couple of moments, you realize that, well, if the clique that you put inside the graph is bigger than the largest naturally occurring clique, the largest clique that occurs at random, then basically you can just find it using enumeration, right? You just enumerate all the cliques of the right size and then you're done. Okay, this boils down to a second moment calculation. You can compute the largest clique is of size 2 log n. I think this was the earliest reference is due to Grimmett, but there are all sorts of generalizations for different models, different values of parameters that you can do. But they all boil down to using the second moment method to estimate the size of the largest clique. Again, it's simple to find the clique just using exhaustive enumeration. Let's move to what is actually possible. One thing really that is probably the first non-trivial idea that people had was to use spectral methods. And the spectral method is based on the following simple observation, that if you take the adjacency matrix and split it into two parts, first is its expectation conditional on the clique and then plus something else, then the expectation conditional on the clique is really a rank 1 matrix. It's the indicator vector on the clique times the indicator transpose. This indicator vector is very simple. It is ones where the clique on the vertices which contain the clique and 0 otherwise. So it really looks like a matrix of this form, and now the noise is whatever it is. Now when you look at this, it becomes very natural that you might want to do principal component analysis. So you just use the principal eigenvector of A normalized appropriately to as an estimator for the clique. The efficiency of this method really depends on the signal to noise ratio in this regime. In this case, the signal to noise ratio is the ratio of spectral norms. So it's the spectral norm of the signal divided by the spectral norm of the noise. The spectral norm of the signal, the one-line calculation is proportional to the size of the clique. And the spectral norm of the noise is of order square root of n by very standard methods in random matrix theory. So intuitively, if k, which is the size of the clique, is much bigger than square root of n, then your principal eigenvector gives you a good estimator which you can clean up. And this was the work that was done by Alon Krivelevich and Sudakov in 1998. There is a more fine version of this phenomenon. Really, this is much more recent work in random matrix theory. And what happens is a certain phase transition of the following kind. If k is a little bit smaller than 1 times square root of n, then if you plot a histogram of the eigenvalues of the adjacency matrix, it looks like this semicircle on the left. So it looks exactly like the Wigner semicircle. And in fact, what you can prove is that the principal eigenvector is asymptotically uncorrelated with the clique. In fact, you can do even more. The correlation is as though it is random, effectively. Okay. On the other hand, if k is bigger than 1 times square root of n, a little bit bigger, then one eigenvalue pops out of the bulk of the spectrum, and the eigenvector that corresponds to this eigenvalue, which is the principal eigenvector, is indeed non-trivially correlated. You can at least hope to get an estimator that might work. Okay, there are many versions of this result. They're called spiked Wigner models in probability theory. The most advanced result that I know of is a remarkable paper by Knowles and Yin, but there are many results by Soshnikov, Baik, Benarus, Pesce, and others in the field. Okay, so here is the first result that I'd like to talk about, which is something that really breaks beyond the spectral barrier, which is that like the result is that there exists an algorithm that will work if k is bigger than square root of n over e. So strictly improves over the spectral barrier of 1 times square root of n. And moreover, this really works in linear time, I mean, essentially linear time in the data, because the data is an n by n matrix, so there are n square somehow bits of information. So what is the key observation that makes this possible, which is that there is a little bit more structure that you can take advantage of. And the structure is that, well, the signal was of course rank 1, but it is in fact also sparse. So you can try and take advantage of this extra information. And indeed, PCA is completely agnostic of this sparse structure. PCA does not care whether the rank 1 component is sparse or not. So this observation was also used by Philippe and others in doing reductions to the hidden clique problem. And there's various, these are just a small sample of the references that do reductions from other machine learning and estimation problems to the hidden clique setting. So you can set up a complexity theoretic reduction in the usual sense. Okay, so how do we take advantage of this? Let's consider the first, the simple way to compute the principal eigenvector is just the power method. Okay, so I'll start with an estimate v0 and iterate vt plus 1 is a times vt times the normalization factor that makes my life a little bit easier. Okay, since vt is supposed to be your estimate for the clique, maybe you want it to be sparse because you know a priori that this is sparse. So let's try and do the following. Instead of using the power iteration as before, I'll do a nonlinear version. And the nonlinear version is that instead of applying a directly to vt, I'll apply it to a function of vt. And this function, for simplicity, I'll just take it to be a coordinate-wise separable function. So just think of the function as I take some thresholding operator, for instance, and apply it to each entry of vt, and then hit it with the matrix again. And then I keep doing this. Okay, this is a simple idea. And what obviously you would want to do is to choose ft, which is some kind of thresholding function that that tries and enforces this sparsity in some way. Okay, so for the next few slides, I'll do a wrong analysis, but we'll see why it's wrong. Let's write out the ith coordinate of vt plus 1. The vt plus 1 is 1 over square root of n, that was my normalization factor, times the sum over j aij ft vtj. Okay. This is just the matrix multiplication written out.
So this is an 82-page paper that you're giving us.
Sorry?
Nothing.
Likely. I don't know what was the last count, honestly.
Yeah, okay. I was thinking, oh, I'll just follow along in the paper, but I guess not. Okay.
I wouldn't recommend it. There is a reason there is a wrong in the title.
I prefer wrong and short than correct and
So yeah, so I think this is something. So this is something that I think that physicists say that that a wrong calculation is better than no calculation. So let's go with this one for a bit. Okay. So you now when you look at this sum and you remember that aij's are these random signs. When I look at that sum, I feel like applying the central limit theorem. Okay, so maybe let's just try and apply the central limit theorem for vt plus 1I. This tells me the normalization is basically correct. So vt plus 1 of I should be approximately Gaussian. Since all of the aij's are random signs if I is not inside the clique, this should be Gaussian with mean about 0, and variance basically the sum of squares of the coefficients. Okay. This prescription also works for the previous iteration. So since vti is also Gaussian with mean 0 and some variance, you can write down what the variance recursion is. So you can write down this variance at the next iteration based on the variance at the first iteration. So you get some recursion for sigma t. And it's a simple recursion that is based on the function ft that you use. Okay. Instead, if I is inside the clique, something almost similar happens, except that there is a small tweak. Since all of the aij's are not random signs, some of them will be all plus 1. The ones, because this vertex is going to be connected to all of the ones inside the clique. So those ones do not have random signs, they're all plus 1s. So that accumulates into a mean term, but then the rest of the stuff is the same as before. Okay, so you can similarly have a recursion for the mean, and this is proportional to the ratio of k over square root of n times some similar expectation that depends on the mean variance parameters as before. Is this okay? Does anybody know why this analysis is wrong?
Some iterative algorithm?
Okay.
I mean, are you worried about
dependence between
Exactly. You cannot apply the central limit theorem, right? The aij's, after at least the first iteration, the vtj's are also complicated functions of the aij's, and they are not independent of the aij. So you cannot apply the central limit theorem, it's just wrong. Let's persist for a bit. We'll see a little bit later how one eventually fixes this. So in pictures, what you have is this following histogram. If I plot the histogram of the vti's, what you get is that the ones not belonging to the clique form this big Gaussian of a certain variance, and the mean is centered at 0. And instead, the ones that are inside the clique are a similar Gaussian, but much smaller in number, and those are situated at a mean that is away from 0. When you look at this, what you want to do is to push the mean as far away as possible from 0 and make it as far in comparison with the variance so that you can just maybe cut in the middle and remove the clique. Okay. So these are the equations or the recursions that I will call state evolution, but it basically describes the state of this algorithm. And you know, what is nice about this is that it tells you what the optimal function is. This is a simple Cauchy-Schwarz inequality. You can normalize the variance to 1 and then optimize which is the function to use, and what you get is a recursion for the mean parameter. Okay, and the recursion for the mean parameter is nice because now this tells you what really happens depending upon the ratio of k over square root of n. Because if k over square root of n is bigger than 1 over square root of e, you don't have any fixed points. So if you start at the, you always start at the origin. This is mu t plus 1 in terms of mu t. You start here, you go up to the curve, you come back, you go up to the curve, you come back, etc. If there is no fixed point, you will essentially go all the way to infinity. On the other hand, if k over square root of n is smaller than 1 over square root of e, you have non-trivial fixed points, and then this you will just saturate at the fixed point. You will never be able to recover. Okay, so the analysis is wrong, but the theorem is right. And what really makes the theorem possible is that you have to change the algorithm a little bit. Instead of using the usual power iteration, what you have to do is, or nonlinear power iteration, you have to do it with what you would call a cavity removal. And this is inspired from the belief propagation heuristics that has been used in machine learning and in statistical physics.
Do you know if the original algorithm just works? I mean, do you need this just to analyze it, or do you need these things to actually make it work?
So the original, without the cavity removal, the state evolution predictions are false. So you cannot, so the recursion does not describe the original algorithm without the cavity removal. With the cavity removal, the dependence problem that we had, that you mentioned before, actually gets resolved, at least asymptotically. Okay, so there is also a lot of, recently there was some follow-up work by Bruce Hayek and others which applied this stuff to some other sparse graph estimation problems. Okay, so at this point I'll just sort of summarize the picture that we kind of know, which is that statistically you just need k to be of order log n, and you can do exhaustive enumeration, which is quasi-polynomial time here. On the other hand, for most of the computational, all of the computationally efficient ones require k to be at least a constant times square root of n, including our algorithm. It didn't really improve over the spectral algorithm by more than a constant.
And is this n squared log n the right?
So you can actually reduce this constant as much as you want if you sacrifice in the exponent of n. That is a nice trick that is actually even there in Alon's original paper, but the fact is that in reality you will never want to apply this to any algorithm, any data set, because what it's asking you to do is to look at pairs or triples of all pairs and triples of vertices, and this is never a good idea to do on a real data set.
How about the other direction? Is n squared? Can you do better than n squared in any cases?
There is an algorithm that is order n squared, which is due to Yuval Perez, I think Yael Dekel and Ori Gurelgurevich. I don't know. I think their constant is something like 1.6. I don't know whether it is sharp.
Is it possible, like in some RAM model or something, to do it in O of n, or is it clear that it's?
I'm not sure. I think the n square usually just comes from doing some sort of eigenvector, like some sort of power iteration. Usually all of them are iterative algorithms, which look very similar to the power iteration with a few extra tweaks of some kind or the other.
What do they assume in the Paris et al. Algorithm is different from your assumption?
I'm sorry,
So
what assumption?
They do it in n squared, but they do it for what?
Instead of n squared log n.
Yeah, so the log n we require for okay, so I did not talk about this, but in reality we can do the analysis for the cavity modified power iteration only for a constant number of iterations. What you need to do is to do a spectral cleanup after that. So the log n comes from doing the usual power iteration for finding, but it's just on a much smaller matrix.
But so is the Paris result stronger than yours?
The constant is weaker, and there is a log n. The constant is weaker, but the log n is a bit better. Yeah. In practice, in reality, I think this result goes through. I mean, if you actually run this thing, 20 iterations is fine.
It's going to be much more.
Yeah. You can run this thing for 20 iterations, and for instance, the simulations in the paper, I did not do the spectral cleanup. We just did the usual algorithm, run it for a few iterations. It's done. So, okay. Okay, so this brings us to the question, really is this regime hard? And for what algorithms can we hope to prove it? So I'll spend a little bit of time talking about the sum of squares approach, which is really a powerful idea for general polynomial optimization. This has become extremely popular since the work of Parillo and Lasser in the early 2000s, but was also present in the literature since the late 80s. What is the sum of squares? They're really a principled way of constructing a sequence of nested convex approximations. You have a difficult convex set and you construct outer approximations in a nested fashion. And they seem to unify many different other ad hoc versions of doing convex relaxations or other versions that were used in combinatorial optimization, such as the Lovász-Schreiber and the Sherali-Adams hierarchy. And they have very interesting consistency properties, which we won't go into, and they're also being convex relaxations, they're also somehow naturally robust. You know this, that all statistical models are not always correct. There's always something that is left unexplained, and you don't want your algorithms to be extremely dependent on the model, because that means when you apply it to some data, it will just give you some nonsense result. So convex relaxations are a nice way to make these robustness properties happen, and the sum of squares relaxations have some natural robustness and monotonicity properties that make them a very good class of algorithms to consider. And really the third is that if you prove something about the sum of squares, even a CS theorist would be interested. Some of them are obviously here, but really it has been extremely well studied over the last 10 or 15 years in the CS theory community. So if you want to prove unconditional results, if you want to prove a hardness result about a specific class of algorithms, I would wager this is a decent one to think about. Okay, so what is the polynomial optimization problem? For each vertex in the clique, you attach a Boolean label, which is 0 or 1. So, I'm sorry, for each vertex in the graph, you attach a Boolean label that's 0 or 1. 1 indicates membership inside the clique, and 0 is membership. 0 means it is not inside. So you want to maximize the size. You just want to find the largest clique, subject to, well, the Boolean constraint, and the second constraint that the support of X must determine a clique. And the way you can enforce this is that for every pair of vertices that is not connected, you enforce the product of the variables to be 0. So it cannot be that both of them are 1. Okay, this is natural. The key idea of the sum of squares is, or one way to look at it is that you don't want to optimize over points on the feasible set of X. Instead, you optimize over probability distributions that are supported on these points. Okay. Moreover, and this is key, you represent these probability distributions using just a small number of moments, and you enforce only a few of the consistency conditions that these moments are supposed to have. Okay, so this will be a bit of notation that I really need to set up, but n in braces is the first n integers. N choose D will be the set of subsets of size exactly D. N choose less than D is the set of subsets of size at most D. And the decision variable is something that takes a subset of size at most D and spits out a number between 0 and 1. Okay, and the interpretation that I want you to keep in the back of your mind is that this number is kind of a probability or a moment of some under some appropriate distribution. This is not exactly right, but it's a useful mental model to have. So what is the SOS program? You want to maximize the mass that is assigned to the singletons. This is analogous to the size, subject to a few constraints. The first is just normalization, corresponds to probability distributions integrating to 1. The second is the constraint that enforces the clique part, which is that if x, if a subset of vertices in the graph does not induce a clique, then x must assign it 0 probability or 0 value or 0 mass. And the third is really the most important constraint, which is that a certain moment matrix that is a linear function of x, this must be PSD. And what is this moment matrix? It is a matrix where every row and column corresponds to a subset of size at most d, or okay, a subset of size at most d over 2, and the entry corresponding to the row S1 and the column S2 is simply x applied to the union of S1 and S2. Okay, so this is a bit of a, this is a little much, but let's just look at a picture. So let's look at the case when d equals 2. It's convenient to think of d as a even integer. So if you look at d equals 2, you have the moment matrix where every row and column corresponds to a subset of size at most 1. So you have this null set, and then you have all of the singletons, right? So you must assign something to the null set, you must assign something to all of the singletons, and you must assign something to all of the pairs. So let's talk about a specific test. So I'll call SOS-GD the optimum of the SOS program when it is run on D, on the graph G. And what I will do is I will just declare that the alternative hypothesis is true if this SOS program is bigger than K. Otherwise, I will declare the null hypothesis to be true. The rationale for this test is very simple. Imagine that instead of the SOS program, I had an oracle that computed the true optimum of the program. If I had that oracle, then this would be the right test. What I'm doing here is just replacing that oracle with a sum of squares relaxation of the oracle, which is computable in n to the order d time. Okay, so this is the main result. It's a result for d equals 4, and this is the first somehow non-trivial level of the relaxation, which goes beyond the spectral methods somehow, which is that this particular test fails when k is smaller than n to the 1 over 3. And the twiddle means that I'm ignoring a few log factors, because I think Boaz might agree that what are a few logs between friends? I'm not even sure how many log factors I'm ignoring here.
It depends on how good of a friend you are.
Perhaps. So independently, there was work by Raghu Meka, Aaron Potichin, and Avi Wigderson, and they proved a slightly more general result, or a more general result which said that the same test, but for general D, failed if k is smaller than n to the 1 over d. If you compare it, there's obviously more general because it goes beyond d equals 4, but for d equals 4, it is a bit weaker. Again, I'm ignoring log factors here. Okay, so some comments that I would like to make. In reality, if you believe that the problem is hard, you would want to prove that for any constant d, the sum of squares test really fails at the threshold of square root of n times maybe something that might depend on d. There was a very nice paper by Raghu Meka and Avi Wigderson in 2013 that claimed this result, and really they set up a lot of machinery that all of us used later on, but unfortunately the matrix concentration methods that they used failed for very subtle reasons. It took a while also to find counterexamples to their proof. It took a while to find even counterexamples to the bug. So but it's still a very beautiful paper, and what got us interested in this problem. But just a couple of months after we wrote our paper, there was a very nice observation by two independent groups. One is Prasad Raghavendra and his student Salil Shram in Berkeley, and Hopkins, Kothari, and Potochin, who are at MIT and MSR respectively. And they improved our result to essentially the optimal exponent of square root of n. It requires really one or two important observations beyond what we did. So it's a very nice set of results. Indeed, the Hopkins paper has a little bit more, and so they prove something also for the general D. Okay, so if you have, are there any questions about this?
Sense in which the particular tests that all these theorems are analyzing is provably optimal among statistical tests that use the degree D SOS relaxation?
It's a good question. There is nothing, okay, there is really nothing of this sort that's exactly in this setting. There is some work by David Steurer and his students on a related problem on that's related to tensor PCA. And what they show in that paper is that if you have at one level a second order effect or a lower order effect that is present in the relaxation, and you do one more step of the relaxation, this becomes a leading order effect. So I'm not sure whether one can prove that this particular test is optimal. Maybe what one can hope to prove is that if the test is suboptimal, perhaps increasing the order by 1 or 2 or a small constant number of, by a small constant actually removes this suboptimality.
I mean, I think it's very subtle how to define this question, because in particular, you could say that the SOS solution also gives you the graph itself. You could recover from that all the edges of the graph. So information theoretically, it also determines exactly whether there is a clique or not. So you have to be a little bit careful in how you define what it means for a test. What kind of information do you allow a test to use? Is it just the actual value? Is it the full moments? Or
I mean, even in the first part of your talk, just using the bulk of the distribution versus the actual eigenvectors with some nonlinearity was already very different, right?
I think there is a result that shows that no test based only on the eigenvalues can work, irrespective of whether it's polynomial time or not. Right. But that's not for this model. That's for a slightly different model. It's for the Gaussian version of this model. Okay, so what is the proof strategy? It's fairly intuitive. It's the following observation: is that if you think that the relaxation is good, you would think that, well, the SOS value under the null model would be pretty small, and under the alternative model would be pretty large. If the relaxation were good in the sense that it is faithful to the original polynomial optimization. If you think that the relaxation is bad, then all this means that you have to do is that you have to show that the value of the SOS program is large under H0 or under the null model. Okay, so this is a maximization problem. One way to show a lower bound on the maximization or the value of the maximization problem is just to guess a solution and compute its value. So that's what we are going to do. We're just going to guess a solution. We'll prove it is feasible, and then we'll compute its value and see what happens. Okay, so before going to the d equals 4 case, I'll just spend some time on the d equals 2 case, and we'll actually do a proof here. So I think there was a quote that I heard only the first part of, which is that every talk must have a proof and a joke. There is a second part to this quote, is that they must not be the same thing. so, so this is the proof part. So, okay, recall that we had this moment matrix. This is for d equals to something that has rows and columns that are indexed by subsets of size at most 1. So, just the null set and the singletons. So, recall what are our constraints. You want to set x v equals 1, so there's nothing to guess there. If x of s is if s is not a clique, then you must set x of s to 0. So, for instance, if a pair of vertices is not connected, you must put 0 over there. Does anybody have any guesses for what you want to put on the singletons and on the pairs? Okay, I'll take the simplest possible guess, right? You want to put something for the singletons and something for the pairs. If the pair is not connected, you must put 0. So, there is some multiplier alpha that depends on the pair and that depends on the singleton. Let's just take it independent of which one it is. So, I'll just put one value if it is a vertex and one value if it is a pair, if it is an edge, and for the non-edges, I just put 0, right? So, basically what I get is alpha 1 times 1 on the outer products, and inside I have alpha 1 times identity, and then there's alpha 2 times the 0, 1 adjacency of the matrix, which I will call script G. Okay. Now, the question is, now the linear constraints are, by the way, automatically satisfied, so you don't have to worry about them at all. All you now need to do is to show that the moment matrix is PSD. Okay. So, when I look at this, I wanted to do the Schur complement immediately. So, let's do it. The first part is the alpha 1 times identity plus alpha 2 times 0, 1 adjacency matrix. And then you have to subtract the Schur complement, which is the outer product of the factors. You get a value alpha 1 squared times 1, 1 transpose. You want to show that this matrix is PSD. Let's look at it in expectation. In expectation, the graph just becomes an alpha 2 times 1, 1 transpose, because each vertex is connected with each edge is connected with probability 1/2. So you just get alpha 2 over 2 times 1, 1 transpose. And since you want this to be PSD, it makes sense to use the 1, 1 transpose factors to cancel each other out. So we'll put alpha 2 over 2 minus alpha 1 squared to be bigger than 0. This is one condition. The second condition comes from the fact that there is a deviation indeed. So we'll use the identity part that was left over in the earlier equation to cancel out the deviation. The deviation is just alpha 2 times G minus its expectation. Okay? So if you set alpha 1 bigger than the spectral norm of G minus its expectation, you're done. This again we can prove is about of order square root of n using very standard results in random matrix theory. So you have alpha 1 is bigger than alpha 2 times square root of n. Okay, so this is the second condition. You can put them together because you have an upper bound on alpha 1 in terms of alpha 2 and a corresponding lower bound. These must be consistent. So if you solve it, you get with a one-line calculation that alpha 1 is supposed to be at most 1 over square root of n. Under H0 or under the null hypothesis, the value is, or the value of the maximization problem is at least the value of this solution. The value of this solution, you recall, is just the sum of the mass on the singletons. So I have n vertices, and for all of them I put alpha 1, so I get about square root of n. Okay, so what did we really prove? We reproved the result by Feig and Krautkammer in the early 2000s, which is that this test fails to distinguish between H0 and H1 when k is about of order square root of n. Okay. Before going to d equals 4, I think we would like to just go over the key ingredients for d equals 2, which is that firstly we had a very simple choice for x. Then we analyzed its expectation. There was some sum of orthogonal projectors, there was something along 1, 1 transpose, something orthogonal, etc. And then for the deviation, we could use standard results that were already known. You can use the matrix concentration results. You can use the moment method that goes back to Wigner. You can use epsilon net arguments, which are, I think, first used by Friedman, Kahn, and Semeredi for random graphs. You can use all of these things. The thing that changes when d equals 4 is that really each of these steps becomes a little bit more complicated. So the guess is kind of similar in the sense that what you want to do is to take x that is proportional to the indicator that a particular vertex is a clique, and then the proportionality constant, we just make the simplest possible assumption of choosing it to be just dependent on the size. So it's something if it's a vertex, something if it's a edge, something if it's a triangle, and something if it's a four-clique. Okay, and again, linear constraints are automatic. All that matters is the PST constraint. And that gives us conditions on these alphas. Okay, so this is the moment matrix for d equals 4. It has about n to the 4 entries, and but instead of looking at this large messy matrix, I'll just concentrate on the sub block that is indexed by the pairs, and see what happens to each of our steps for this sub block. It illustrates basically the main difficulty. The expectation you can instead of having just 2 orthogonal projectors, you have actually 3 orthogonal projections, and they have actually very widely differing eigenvalues. Really, the point is that the eigenspaces corresponding to these eigenvalues relate to irreducible subrepresentations of the symmetric group. This is because this expectation is invariant to changing relabeling the vertices. So that's why this kind of naturally comes up. But the eigenvalues are very differing. So you really need to understand these symmetries and take advantage of this fact, especially when you consider the deviation part. Okay, when you look at the deviation, it's an n squared times n squared matrix. So it has n to the 4 entries, but is dependent only on n squared random bits. Okay, so all of these entries are highly dependent. Okay, and because of that, the behavior is very different from classical random matrix ensembles, in the sense that some of this matrix actually has an unusually high spectral norm based to the compared to the prediction that you would make without taking the dependency into account. So how do we make it work? Really, you just decompose the deviation into pieces. You control each piece separately, and you try and align the pieces which have large eigenvalues or a large spectral norm with the eigenspaces that are large. And this requires you to understand the symmetries of what is happening. We'll not go into this in detail, but I'll just end with a couple of, before I finish this section, I just want to mention a few open problems. So the question remains whether we can generalize this to other models. If k is smaller than square root of n, proving that this is hard for d bigger than 4 is still open. The last time I said this, I had bigger equals 4, and then like 2 weeks later, the bigger equals became wrong. Maybe this time, maybe this time they will do it for d bigger 4. Okay, and of course, it remains whether you can come up with stronger hardness proofs. Okay, I'll just spend a couple of minutes talking about a few other things that I've been thinking about over the past few years. The hidden clique problem is also very interesting because it's related to structured versions of principal component analysis, particularly sparse PCA. So we had there was work with Andrea in which we analyzed covariance thresholding, which is an algorithm, and what you can do is really go beyond this standard STP that people usually use for sparse PCA. With Emil and Andrea, we had another paper which considered even more general versions of this, where the factors of the principal components were constrained to be in a cone, in a convex cone. So for instance, non-negative PCA is an example of this. More recently, there has been a lot of work on stochastic blocker models from a variety of different communities. So this was a paper in which we proved a couple of things, but I think the most interesting part about this result is firstly a universality portion, where you prove really that the asymptotic mutual information is invariant, is essentially independent of the specific random model that you use. This is similar to universality results in random matrix theory, where say the spectrum does not depend on whether you have Gaussian entries or plus minus 1 entries, etc. And the second part of the result is rigorous verification of what in physics is called the replica symmetric ansatz. I won't go into that in detail here. Lastly, I just want to mention some things that are that I'm thinking about now, or that I think would be very cool to tackle. The first is, still related with PCA and structured versions. Is that if you see the use of these things, especially in nowadays, it's popular in medical literature to combine data from many different past studies and then do a joint analysis. Unsupervised methods like PCA, clustering, all these kind of things are used a lot in such studies for a variety of reasons. People want to do pre-processing of the data. You want to extract features. You can use the principal components as certain features or the clusters as features. And really, they also formulate different hypotheses based on this. So I think there are a couple of challenges that I find that would be cool to think about. First is obviously, for clustering and for structured versions of PCA, we don't necessarily have great algorithms. So can we do this in polynomial time, or can we come up with fast and reliable algorithms? And the second, is important for particularly scientific applications, is that can you do uncertainty assessment? Can you build confidence intervals? Can you assign p-values to the estimates that you get? Because it's important when you try and use these things for medical studies. And the second is related to the sum of squares results. When I learned this stuff, by the way, I strongly recommend Boaz's lecture notes. They're fantastic. When I read those notes and started learning about this, I found it really cool. But in reality, if you try and program these sum of squares algorithms, they are very difficult. And this is because it gives you a humongous STP, which is not easy to solve. So, but there are some ways in which you can think about using these in practice as well, which is a lot less done in the community than, say, for instance, lower bounds using SOSR in the CS theory community. And one example I think that would be nice to do is use this in graphical models. Graphical models are widely used for a variety of different things like image segmentation, error correcting codes, etc. This is a book by Daphne Kohler, who is a professor at Stanford. I think it is about 1,200 pages of examples of graphical models. So very nice book. So there's about three important things that you want to do with a graphical model. Broadly, you want to sample from the model. You want to marginalize variables based on the others. So say you're given some diagnostic information, you're given symptoms, you want to know what disease it is. You can think about marginalization. And the third is computing partition functions. All these are roughly equivalent, and one can think about computing partition functions as a general version of all of these. Really, there are two popular methods that people use in practice. There's variational methods where you come up with versions of the partition, approximations to the partition function and try and compute it. Belief propagation and other versions are similar. Unfortunately, they yield only approximations. For instance, you don't get rigorous upper and lower bounds. Moreover, these are notoriously difficult to analyze, especially for general graphical models. I think the sum of squares methods can provide a way to actually computing these or coming up with rigorous upper and lower bounds for these things. They give you a knob. It's a rough knob, but at least they give you a knob to trade off between accuracy and computational requirements. And the consistency properties of these sum of squares are, I think, closely related to what are called Kikuchi approximations in physics. So I think there is a lot of work that can be done in this area. So thanks for your attention, and I'm happy to take questions. Yes.
Is there a sense in which the 1/√E threshold in the first part of your talk is optimal for that class of algorithms?
Excellent question. I suspect it is, but I'm not sure yet how to prove it. One version of the result that we have is that instead you consider the same problem on sparse graphs instead of dense graphs. And for that, we can prove that it is optimal. It's optimal for local algorithms. So if you consider the problem on a sparse graph, there is a sense of locality in the usual sense, right? Locality of So for all local algorithms, wherein where the node makes decisions just based on a bounded size neighborhood around it, this 1 over square root of e is an optimal threshold. Beyond that, I'm not.
So is that because we don't have very good tools for understanding like belief propagation, other iterative algorithms, and dense regimes? Is that the reason why some of the limitations for local algorithms don't translate to dense settings?
But there is no good sense of locality on a dense graph, right? I mean, in reality, the graph. In reality, the graph that you must think about in the dense case is actually the complete graph. So every vertex has all of the neighbors in its neighborhood. Now, the sum of squares was actually one other reason that I'm interested in sum of squares is that it gives you a notion of locality which is really based to the moments. We're using only a few moments, so maybe that is one notion that one can think about. The other thing is that this trick of Alon where you can reduce the constant by improving by trading off the exponent. So clearly it can only be done, say, for some linear time algorithms of some sort. This seems to be an even harder problem than anything else. So I'm not sure, but yeah, it's a very interesting question to think about. Yes.
One could imagine a variant of the planted clique problem in which someone gives you maybe a hint as to which nodes are correct or not. Maybe you hire a biochemist and they flag certain nodes as being more likely to occur. Are you aware of work in this kind of hint model? Is it obviously easier, or is anything known?
It's a good question. This constant reduction trick is very closely related to what you said. Really, you just guess which pair of vertices and then reduce the graph to all of the common neighbors of this this set of vertices. That improves the signal to noise ratio that you have there. The thing is that in real application, so okay, it's a very neat trick, but I really don't like this trick very much for a number of reasons. First, that you cannot run it. Secondly, on real data sets, it's hard to decide what is the right common neighborhood, because that depends on the threshold. In reality, you would just want to do something that takes advantage of all of the weights. So for instance, if it was not a completely connected, so if the clique was not completely connected, but say was Erdos-Renyi with some probability p that is strictly less than 1, it's not clear how to do exact versions of this stuff. So I would suspect that I don't know of any work that really goes beyond.
In some sense, you could probably incorporate this into the sum of squares framework, but just saying like you just measure the objective function differently
For those vertices.
So if you had scores, if you had a score for every vertex, you try to maximize the score rather than to maximize the clique size or something.
Right.
So those alpha i's.
Right. So yeah. So that's an excellent point. For instance, one way to do it is that instead of having the sum over all of the singletons, you had a weighted sum, and perhaps you put large weights on the ones that you think are more likely. Maybe this would work. I'm not sure of anybody who has actually used something of this kind, but it's a wonderful thing to think about.
You can get more questions from them if you. We're supposed to be on a phone call that started at noon.
Sure.
So we will see you later today, and Henry is taking over and hosting you.
So are there? Oh, thank you.